There is a type of wind event that can match a Category 3 hurricane, stretch 300 miles wide, and sustain itself for 12 hours across 700 miles of ground. It has produced the costliest thunderstorm in American history, and when it's bearing down on your neighborhood, there's a 90% chance your phone won't buzz, the siren won't sound, and the warning system that's supposed to protect you won't activate, because every automated defense this country has built is triggered by rotation, and this wind doesn't rotate. It moves in a straight line. The warning infrastructure protecting 53 million Americans on the I-95 corridor was engineered to detect one kind of wind. The atmosphere keeps delivering another, and the gap between those two things is killing people inside warning polygons they received but didn't understand. If the gap between a tornado warning and a severe thunderstorm warning just grabbed your attention, take a second and hit subscribe to Orbital View. We're tracking the warning architecture that decides who gets alerted and who doesn't, and that story is moving fast. Drop a comment with this. Have you ever been in a derecho or a straight line wind event and had no idea what was happening? Your city and what year? I read everyone. The physics of a storm line that acts as a planetary plow, a river of cold air descending from 40,000 feet and slamming the ground at 110 miles per hour across a front 300 miles wide. The night the lights went out in Washington, how the 2012 derecho killed people inside warnings they received but didn't take seriously. And the number from NCAR that nobody is talking about, the geographic footprint of these events has grown nearly fivefold in 40 years. Let's get into it. Part 1. The wall nobody warned you about. On June 3rd, 2026, the Storm Prediction Center in Norman, Oklahoma, posted language in its Day 1 convective outlook that stopped me mid-scroll. The discussion described a cold front pushing through the Great Lakes and Ohio Valley, storms expected to consolidate into one or more large-scale thunderstorm complexes, and transition to and this is the SPC's language, not mine, linear mode with a continued risk for damaging winds. Buried a few lines deeper, a sentence that reads like operational boilerplate, unless you know what it means. A QLCS circulation or two is possible, but the wind threat should be the main concern. If you don't read SPC area forecast discussions for a living, that sentence probably doesn't register. It should. Linear mode and the wind threat should be the main concern is the forecaster's way of flagging exactly the kind of event this entire video exists to investigate. A type of storm system that doesn't rotate, that the siren infrastructure wasn't designed to communicate, and that the public has no cultural framework for interpreting. The corridor, in its projected path, the Ohio Valley into the mid-Atlantic, threading the needle toward the most densely populated stretch of interstate highway in America, is the same corridor that keeps getting hit. And the reason I'm spending time on SPC discussion language is because it's the first layer of evidence that the professionals who watch this atmosphere for a living see these events coming, flag them in technical language, and then watch the communication chain fail between their forecast and your front door. This isn't isolated. In May of 2024, a derecho hit Houston, 100-mile-per-hour winds, 8 dead in Harris County, 2,500 skyscraper windows blown out in the downtown core, power out for weeks in some neighborhoods. A month later, in June of 2020, a separate derecho killed 4 people and knocked out power to nearly 1 million customers across Pennsylvania and New Jersey. And then 13 months before, that SPC outlook I just read you, on April the 29th, 2025, a fast-moving derecho tore across the Ohio Valley and slammed into western Pennsylvania. You can pull the data yourself. It's archived on the NWS Pittsburgh event page. Pittsburgh International Airport recorded a gust of 71 miles per hour. That is the 3rd strongest gust ever measured at that station. Latrobe, about 40 miles to the southeast, clocked 79. And in Allegheny and Beaver counties alone, Duquesne Light Company, the primary utility serving the Pittsburgh Metro, reported more than 240,000 customers in the dark, with over 20,000 individual hazard incidents logged in the first hours. Downed wires, transformer fires, trees draped across every arterial road, 20,000 incidents. Across the broader affected region, 700,000 people lost power. Duquesne Light's public statement used a word I want you to hold on to: unprecedented. At least 3 people died. One, near St. Martin, Pennsylvania, was electrocuted by a downed power line, not during the storm itself, but in the aftermath, while trying to navigate a world the storm had rearranged overnight. And here is the thing about those 700,000 people in the dark. Every one of them had received a severe thunderstorm warning. The NWS offices covering western Pennsylvania issued the warnings with lead times that by the agency's own performance standards would be considered adequate. The information reached the population, and the population was caught completely off guard. Not because the warning didn't arrive, because the warning didn't mean what they thought it meant. I've spent weeks on this, pulling apart the service assessments, the detection statistics, the building codes, the climate projections, the peer-reviewed literature that the public has never seen. And the conclusion I keep arriving at doesn't live inside the atmosphere. It lives inside the system that's supposed to translate the atmosphere into action. The warning infrastructure protecting the most densely populated corridor in America was engineered to detect the wind that spins. And the most destructive wind event the atmosphere actually delivers to the eastern seaboard doesn't spin at all. Every one of those 700,000 customers received a severe thunderstorm warning. Every one of them was caught off guard. The question is why, and the answer lives inside a distinction that most Americans have never thought about. Part 2, the distinction that decides who gets warned. There are 2 warnings the National Weather Service can issue when dangerous wind is approaching your location. One is a tornado warning. The other is a severe thunderstorm warning, and most people assume the difference between them is a matter of degree, that a tornado warning means more dangerous, and a severe thunderstorm warning means somewhat dangerous, but not as bad. That assumption is wrong in a way that has killed people. The difference isn't about how dangerous the event is. It's about what happens inside the alert system after each warning is issued. The mechanical difference. The wiring, not the weather. And that mechanical difference is the gap this investigation is built around. When a tornado warning goes out, 2 things happen automatically. First, your phone buzzes. If you have a cell phone with wireless emergency alerts enabled, and the vast majority of Americans do, a tornado warning triggers a WEA message. It comes through even if your phone is on silent. It overrides Do Not Disturb. It sounds an alarm tone you can't ignore. Second, in most communities across the tornado-prone regions of the country, outdoor sirens activate. The ones everybody calls tornado sirens. The cultural signal is total and unmistakable. Get inside, get underground, take shelter now. When a severe thunderstorm warning goes out at the base level, that's 58 miles per hour winds or 1-inch hail. The threshold for what the NWS defines as severe, your phone does nothing. No WEA, no alarm, no buzz. The warning exists on the NWS website. It'll show up on your weather app if you happen to check it. Your local TV meteorologist might break into programming, but the system's automated defenses, the siren, the phone alert, the infrastructure that makes the tornado warning feel like an emergency, don't activate. Now, there's a second tier, and it's only fair to acknowledge it because the NWS has genuinely tried to address the problem. In 2021, August 2nd of 2021, specifically, the agency introduced an impact-based tagging system for severe thunderstorm warnings as part of the Hazard Simplification Project. Considerable for 70 mile per hour winds or golf ball-sized hail. Destructive for 80 miles per hour or baseball-sized hail. Greg Skoor, the NWS Severe Weather Program Lead, helped design the framework in the aftermath of the 2011 Joplin tornado, and the destructive tag does trigger a wireless emergency alert. Your phone buzzes for a destructive severe thunderstorm warning the same way it buzzes for a tornado warning. That's real progress. That's the system patching itself. But here is the number that carries this whole section, and it comes straight from the NWS's own implementation page. On average, only 10% of all severe thunderstorms reach the destructive category each year, nationwide. 10%. That means 90% of severe thunderstorm warnings, including events with 75-mile-per-hour winds that can kill, that topple mature hardwood trees onto homes, that snap power lines across 6-lane highways and launch 2x4s through car windshields, pass through the system without triggering a single automated alert to your phone. No siren, no alarm. Nothing that interrupts your evening the way a tornado warning does. One meteorologist at WHSV in the Shenandoah Valley estimated the destructive tag activates in his coverage area maybe once every 5 to 7 years. Think of the warning system as a velvet rope. On one side of the rope is every automated defense the country has built. The phone alerts, the sirens, the cultural urgency embedded in the word tornado. On the other side is a severe thunderstorm, warning that might appear on your weather app if you happen to look. You can be standing in 90-mile-per-hour straight-line winds the NWS itself says can match an EF1 tornado in destructive potential over a vastly wider area, and the automated defenses haven't activated because the event didn't clear the rope, not because it isn't dangerous, because it isn't rotating. The siren is a cultural artifact, and the culture it speaks to is tornado culture. If the wind doesn't rotate, the siren stays silent. And there's a reason the NWS hasn't simply lowered the destructive threshold or added a new WEA category for non-tornadic wind, alert fatigue. In 2019, the agency scaled back flash flood wireless emergency alerts to only the considerable and catastrophic tiers, because too many alerts were causing the public to tune out all of them. The same institutional pressure, the fear that more alerts leads to less compliance, acts as a brake on expanding WEA triggers for straight-line wind. So the system knows the gap exists, and the system also knows that the most obvious fix carries its own risk. That tension hasn't been resolved, and while the institution deliberates, the atmosphere keeps producing events that fall inside the gap. So the system is built around rotation, around the mesocyclone signature on radar that triggers the tornado warning, that triggers the siren, that triggers the phone alert. And the most destructive wind event the atmosphere delivers to the eastern seaboard, the one that blacks out entire states and flattens entire tree canopies and runs up damage tabs in the billions, doesn't rotate at all. It moves in a straight line, and it has a name most Americans have never heard. Part 3, The Anatomy of a Storm Line. I need you to picture something. Imagine a bulldozer blade made of cold air, 50,000 feet tall and 300 miles wide, plowing into the warmest, most humid air mass the continent can produce. The blade doesn't stop, doesn't stall. It moves at 60 miles per hour, and it maintains itself, feeds itself for 12 hours across 700 miles of ground. What you're picturing is not a single storm. It's not a tornado, not a supercell. It's a wall of storms, an unbroken line of severe thunderstorms, stitched together edge to edge, traveling as a single coherent system. That is the thing this video is about. Scientists call it a quasi-linear convective system, QLCS for short. But the term doesn't land until you understand what it does, and specifically what engine it carries inside. Walker Ashley at Northern Illinois University and Alex Haberle at LSU built the first systematic count of these systems using machine learning applied to 22 years of radar data, published in Weather and Forecasting in 2019. Their algorithm scanned for radar signatures longer than about 60 miles and at least 3 times as long as wide, the contiguous core of heavy rain and convection that defines the line. They found over 3,000 of them across the continental United States, 3,000 storm lines in 2 decades, and most Americans couldn't name a single one. Gustav Hinrichs, a physics professor at the University of Iowa, actually coined the word derecho in the 1880s, from the Spanish for straight or direct, to distinguish this kind of wind from the tornado's rotation. The scientific community forgot the word for almost a century. Robert Johns and William Hurt revived it in 1987, and the public didn't encounter it until that wall of storms rolled into Washington in 2012. The engine that makes a QLCS deadly sits behind the leading edge. Behind the bulldozer blade, there's a river of mid-level air flowing from the back of the system toward the front. Cold air, dense air, descending from 30 to 40,000 feet, pulled forward by the storm's own pressure gradient. It channels toward the leading bow of the storm, accelerates as it descends, and hits the surface as straight-line wind. Not rotation, not a funnel. A fire hose aimed sideways. Picture a waterfall, but instead of water falling off a cliff into a pool, it's cold, dense air falling from the mid-levels of the atmosphere and fanning outward when it hits the ground. That horizontal fan is the wind that takes down trees. That's the wind that collapses buildings. Morris Wiseman at the National Center for Atmospheric Research published the foundational work on this mechanism in 1993, a paper called The Genesis of Severe, Long-Lived Bow Echoes that remains one of the most cited studies in mesoscale meteorology. He showed that when you have enough stored energy in the atmosphere, think of it as a compressed spring ready to release at least 2,000 joules per kilogram and enough wind shear in the mid-levels to sustain the plumbing, the storm generates what he called a rear-inflow jet. The jet descends at the apex of the bow, and the bow itself is held together by a pair of counter-rotating vortices at each end. Wiseman called them bookend vortices that act like nozzles on the fire hose, channeling and focusing the descending jet toward the surface. The nozzles don't create the pressure, they aim it, they concentrate it, and the concentrated jet is what produces the surface winds that peg anemometers at 100, 120, 140 miles per hour. So the mechanism is clear. The wind isn't random, it's organized, directed, and self-sustaining. But the part that locks back to the thesis is purely geometry. A tornado path is narrow, yards to maybe a mile wide. Devastating, yes. Precise, localized, intense. A derecho swath. The damage path left by a mature QLCS is something fundamentally different. By definition, a derecho stretches at least 60 miles wide and runs hundreds of miles long. The 2020 Iowa derecho, which I'll walk you through in the next chunk, carved a path across at least 90,000 square miles. That is roughly the area of the state of Oregon. Imagine the difference between a rifle shot and a freight train. The rifle is precise and devastating. The freight train doesn't care about precision. It takes everything in its path. And here's the mechanical problem that makes the thesis real. The radar network that protects you, NEXRAD, the backbone of severe weather detection in the United States, was designed to detect rotation. The algorithms that run on every radar site in the network are hunting for specific signatures. Velocity couplets, mesocyclone patterns, the tornado vortex signature, those are the triggers. That's what the software watches for. Scan after scan, volume after volume, 24 hours a day. And those algorithms are genuinely good at what they do. They've been refined over decades to find rotating storms with remarkable skill. But a QLCS doesn't hand the radar what it's looking for. The wind is there, the destruction is there. The straight line wind field, barreling toward your neighborhood at 70 or 80 or 100 miles per hour, is physically real and physically devastating. But the signature the algorithm was trained on, the spin, the rotation, the mesocyclone, isn't present. It's a metal detector at the beach, brilliant at finding rings, useless at finding the wave that's about to knock you down. Part 4. The detection problem. Two numbers. I want you to hold them side by side because together they tell you everything about why the warning gap isn't a policy inconvenience. It is a structural vulnerability built into the detection layer of the system itself. The first comes from Alexandra Anderson Frey, who published a study in 2016 in Weather and Forecasting, comparing how well the warning system detects tornadoes depending on what kind of storm produces them. For right-moving supercells, the classic tornado machines, the storms the entire detection apparatus was optimized to find, the probability of detection is 78.7%. Nearly 4 out of 5 get a warning with positive lead time. The system does what it was designed to do. For QLCS tornadoes, tornadoes that spin up inside a storm line, the mesovortices I'll unpack in Part 7, the probability of detection drops to 49%. 49, that is a coin flip. Heads, the warning arrives before the tornado does. Tails, it doesn't. And I need to be precise about what this means and what it doesn't, because I'm not going to bend a number to make the thesis land harder. Anderson Frey's 49% describes tornado detection specifically, tornadoes embedded within QLCS. The straight-line winds that cause the widest damage across the broadest area don't have a tornado vortex signature at all, because they aren't tornadoes. They're the rear-inflow jet hitting the ground. The system wasn't built to warn for them in the same way, so the 49% number is actually the optimistic case. It's the detection rate for the rotating hazards inside a QLCS. The non-rotating hazard, the one that does the most widespread damage, sits even further outside the detection architecture. Jeffrey Brodsky published a complementary study in 2013 in the same journal, and his numbers on warning lead time are the ones that unsettle me most. Discrete supercell tornadoes get an average warning lead time of 17.8 minutes. QLCS tornadoes get 12.3. Tornadoes from disorganized convection get 11.7. Those are averages, meaning a significant fraction of QLCS tornadoes have zero or negative lead time. The tornado is already on the ground, already doing damage, before the warning reaches a single phone or a single siren, and then the darkness compounds it. This is the piece I didn't see coming until the data forced it. QLCS tornadoes occur at night roughly 40% of the time. For supercell tornadoes, that number is about 21%, nearly double the nocturnal frequency. The storms that are hardest to detect are also the most likely to arrive when you're asleep, when the TV is off, when the phone is charging on the nightstand, and you're 3 rooms away from hearing it. Ashley's research on tornado fatalities has shown that overnight events are far more deadly per tornado. People aren't watching apps, aren't near a television, aren't awake to hear a siren even in the communities that do sound one. Mobile homes, which are catastrophically vulnerable to any wind event, are overrepresented in nighttime deaths because residents have no visual warning, no sky to watch, no sense that the atmosphere has turned hostile outside their walls. When the most detection-resistant type of tornado is also the most nocturnal, the compounding vulnerability is worse than either statistic suggests alone. And for the straight-line winds, the primary QLCS damage mechanism, the thing that knocks down power across entire states, the nighttime problem is just as severe, but without even the partial safety net of a tornado warning. Because the straight-line winds, by definition, don't trigger tornado alerts. At 2 in the morning, with the destructive tag still covering only 1 in 10 severe storms, the warning gap becomes a chasm. I want to be honest with you about something, because that's what this channel does, and I'd rather lose a clean talking point than lose your trust. I initially expected the data on straight-line wind deaths to dwarf tornado deaths, and the real picture is more complicated. Tornadoes kill an average of about 70 to 80 Americans per year. Per event, they're more lethal. They concentrate their energy in a smaller area. They produce the most violent wind speeds the atmosphere is capable of, and single tornado outbreaks can kill hundreds. But straight-line winds are vastly, overwhelmingly more common, more than 15,000 damaging reports per year versus roughly 1,000 tornadoes. 2/3 of all severe weather reports in the United States are straight-line wind. Not some, not a plurality, 2 out of every 3. The lethality per event is lower. The exposure is staggering. And the warning infrastructure protecting that exposure, protecting that 2/3 of all severe reports, is structurally weaker than what protects against the other third. What happens when a major QLCS actually hits a major population center? That question has been answered more than once. And the answers, when you pull the service assessments and the damage surveys and the post-event timelines, are worse than the detection statistics prepare you for. Because the people who died in the biggest derechos of the last 15 years weren't unwarned. They were warned. They just didn't know what the warning meant. Part 5, the night the lights went out in Washington. June 29, 2012, a Friday, the temperature in Washington, D.C. had already hit 104 degrees Fahrenheit, a record that made the air crackle with stored energy, stacking the lower atmosphere with the kind of explosive instability that atmospheric scientists measure in joules per kilogram, and that everyone else measures in the sweat running down the back of your neck. Several thousand miles of atmosphere were loaded like a spring, and the cold front crossing the Ohio Valley was about to pull the trigger. By noon, Central Time, a cluster of thunderstorms over Iowa had consolidated into a fast-moving wall, a mature QLCS tracking east-southeast at 60 miles per hour. Not a metaphorical 60. Radar-tracked, ground-verified 60 miles per hour, which means the system was outrunning most speed limits on the interstates it was crossing. It had already been flagged by SPC, but here's the institutional detail that tells you how the system processes these events in real time. The Day 1 convective outlook hadn't been upgraded to a moderate risk. That upgrade wouldn't come until 4 in the afternoon Eastern Time, by which point the derecho was already underway, already crossing states, already generating wind reports that would eventually top 1,000. By early evening Eastern Time, it had torn through Indiana and Ohio. At Fort Wayne, Indiana, an anemometer caught 91 miles per hour. Dayton saw 82. Columbus, the same, and the rear-inflow jet, the engine I described in Part 3, was doing exactly what Wiseman's physics predicted: self-reinforcing, accelerating, feeding on the energy the record heat wave had loaded into the boundary layer. Then it crossed the Appalachians and entered the I-95 corridor. The forecasters at WFO Sterling, the NWS office covering the Baltimore and Washington metro area, had been tracking the system for hours. They issued 15 severe thunderstorm warnings and only 2 tornado warnings during the entire event because the threat was not tornadic. It was straight-line wind. They identified it correctly and communicated it through the correct warning product with an average severe thunderstorm warning lead time of 37 minutes. By any operational standard, that is strong work. But here's what 37 minutes of a severe thunderstorm warning looked like on the ground for the population of the DC metro area in June of 2012. No wireless emergency alert. The destructive tag didn't exist. It wouldn't be created for another 9 years. No outdoor sirens. The warning appeared on the NWS website and on weather apps for anyone who checked. Some local television stations broke in with coverage, but this was a Friday evening in summer. People were at backyard barbecues. People were driving home from work on the Beltway. People were at outdoor concerts and baseball games, and on patios across northern Virginia and suburban Maryland. Many had no idea a storm line with 90-mile-per-hour potential was bearing down on them. They found out when the trees started falling. Imagine you're at a neighborhood cookout in Arlington. The sky has been hazy all day. 104 degrees will do that. You've heard thunder in the distance, but the sun is still partially visible. And then within minutes, the wind arrives. Not a gust, a sustained wall of wind that doesn't stop. Trees that have stood for 80 years start snapping like matchsticks. Power lines arc and fall across the street you parked on. The lights go out across the entire block, across the entire neighborhood, across, it will turn out, the entire metro area. You couldn't have been warned by siren because no siren sounded. Your phone didn't buzz because the warning product that was issued doesn't trigger a wireless emergency alert. The 37 minutes of lead time existed inside the NWS system. It did not exist inside your evening. Dulles International Airport recorded a gust of 71 miles per hour. Reagan National, 70. BWE, 66. Those numbers sit below the 80-mile-per-hour threshold that would later become the destructive tag's trigger, but the destruction they produced was anything but marginal. 4 to 5 million customers across the Ohio Valley and Mid-Atlantic lost power. Some wouldn't get it back for more than a week. During a heat wave. In early July, the 911 system in the DC metro area went down. Sit with that for a second. The emergency communication system that exists to connect people in crisis to the help they need, it went offline. During a mass casualty windstorm. During a record heat wave. And here is where the compound story starts to surface, because the storm didn't just knock down trees and snap power lines. It took the electrical grid offline across several states during a week when afternoon temperatures were breaking records. The power outage didn't last hours. In some neighborhoods across northern Virginia, suburban Maryland, and West Virginia, it lasted over a week. And the people who needed electricity to survive, elderly residents on supplemental oxygen, people with chronic cardiovascular conditions, people in housing without backup cooling or the money to get to a hotel, started dying. Not from the wind, From the heat the wind left behind, the storm took the power, and the heat that fed the storm became the second killer. The NWS Service Assessment, published January 2013, assembled by a team led by Michael Vecchio and signed by Laura K. Fergione, is the single most important document in this investigation. I've read it cover to cover 3 times. And the sentence I keep coming back to, the one that carries more analytical weight for this thesis than any other piece of evidence I've found, reads, "A common theme that emerged from talking to emergency managers, media, and the public was that although they received the warnings, they were surprised by the intensity of the winds. They received the warnings, they were surprised. 13 people died directly from the storm, most of them crushed by falling trees while outdoors or in vehicles on roads that should have been cleared. 34 additional people died from heat exposure in the days that followed, during the power outage the derecho had caused. Hold those 2 numbers next to each other. 34 heat deaths, 13 wind deaths. The secondary killer, the compound consequence, the one that arrived after the storm was over, took nearly 3 times as many lives as the storm itself. The warning arrived, the understanding didn't. One more piece about the models, because it connects directly to where the system stands now and what it can and can't do. The operational forecasting tools available in 2012, the NAM, the GFS, the models forecasters relied on to make their calls, missed this event. The service assessment didn't hedge. Those models were of little value in predicting the MCS formation. But one tool got it right. The HRRR, the High Resolution Rapid Refresh Model, which at the time was still experimental, not yet promoted to operational status, depicted the storm complex forming roughly 15 hours before it materialized. 15 hours. Forecasters at multiple offices saw the HRRR output, and they made the rational decision to distrust it, because it was new and unverified and contradicted what the established operational models were showing. The right answer existed inside a model the forecasting community hadn't learned to trust yet, and the system defaulted to the models that were wrong. I don't say that to blame the forecasters. They were making a judgment call with the tools they had, under the protocols they'd been trained on. I say it because it reveals something important about how institutional trust and institutional caution interact when an unprecedented event arrives. The 2012 derecho introduced the word derecho to tens of millions of Americans who had never heard it. And it was supposed to change things, to force a reckoning with straight-line wind as a first-order threat to the eastern seaboard. And in fairness, some things did change. The destructive tag arrived 9 years later. Impact-based warnings were built into the system. The HRRR became operational and is now one of the best short-range convective models on the planet. Those reforms are real, and the people who built them score. The hazard simplification team, the model developers, did serious good faith work. But 8 years after that Friday afternoon in Washington, when the most expensive thunderstorm in American history hit Iowa, the fundamental failure mode was identical. The people in its path had no idea what was coming. The sirens didn't sound, the phones didn't buzz, and this time the scale was something nobody, not the models, not the forecasters, not the emergency managers, not the residents of Cedar Rapids who had never heard the word derecho before August 10th of 2020 had seen before. Part 6, the $11 billion thunderstorm. August 10th, 2020, a Monday morning. If you checked the SPC convective outlook that day, the language would have told you something unusual was developing, but you'd have had to know how to read it. The models were showing a very fast-moving MCS potential across the upper Midwest, with an extreme instability axis and deep layer shear values that were frankly off the charts for a warm season Great Plains setup. At 11:25 a.m. Central Time, the SPC issued a particularly dangerous situation, Severe Thunderstorm Watch. And if you know SPC products, a PDS watch is the agency raising both hands and saying, "Pay attention, this is not routine." The watch covered a corridor from eastern Nebraska through Iowa. The discussion referenced destructive wind gusts and the possibility of sustained surface winds exceeding 100 miles per hour. That language is extraordinary. SPC watches don't casually mention 100 miles per hour. But there was a problem, and it's the same problem that connects every event in this investigation. A PDS severe thunderstorm watch is not a tornado watch. It does not carry the same cultural weight. It does not trigger outdoor sirens. And in August of 2020, the destructive WEA tag, the one that would have sent an automated alert to every phone in the polygon, did not yet exist. It was still a year from implementation. The watch was real. The forecaster concern was real. The automated pipeline that would have translated that concern into a buzz on your phone was not yet built. The system that formed over South Dakota around 8 in the morning was already showing a textbook bow echo structure by mid-morning, the bowed segment of the leading edge that signals a mature, accelerating rear-inflow jet. It tracked east-southeast at speeds that would eventually push past 60 miles per hour, which is important because that forward speed means communities in the path had shrinking windows to respond. And the rear-inflow jet behind the leading edge was screaming, 80 to 100 knots at mid-levels. That's 90 to 115 miles per hour of wind aloft, aimed at the ground, descending through the bow apex exactly as Wiseman's physics predicted. As the system crossed into central Iowa, it began doing something that even experienced severe weather researchers had rarely seen at this scale and duration. It didn't just gust, it sustained. At Cedar Rapids, the damaging winds didn't arrive as a brief pulse and then move on, the way most severe thunderstorm gusts do, a sharp hit, a few seconds of peak intensity, then falling off as the storm races away. They arrived and they stayed. 30 minutes of continuous hurricane-force wind in some neighborhoods. In others, 60 minutes. Not a gust, but a siege, and no American city had experienced anything like it in the modern instrumental record. The measured peak gust at the Atkins, Iowa Automated Weather Station, a small town northwest of Cedar Rapids, reached 126 miles per hour. That is the all-time Iowa state wind speed record from any source. And it was an instrument measurement, not a damage estimate. The damage surveys in Cedar Rapids itself produced estimates reaching 140 miles per hour, which would be equivalent to an EF3 tornado, except an EF3 tornado touches down for minutes and cuts a path a few hundred yards wide. This wind field was 60 miles wide, and it held for an hour. Cedar Rapids lost somewhere between 65 and 75% of its urban tree canopy in that window. I spent a long time with that number. 670,000 trees. Gone. Not trimmed, not damaged in a way that a chainsaw and a weekend could fix. Snapped at the trunk or ripped from the ground, with root balls the size of compact cars, deposited across streets and rooftops and power lines and fences, stacked on top of each other in tangles so dense that chainsaws couldn't reach the bottom layers. In less time than a lunch break, the physical landscape of a city of 135,000 people was fundamentally altered. Aerial photographs taken the following morning show what looks like a war zone, not the pinpoint devastation of a tornado track, but an ocean of debris covering every neighborhood, every park, every commercial district in the city. 95% of Cedar Rapids lost power. The grid didn't just fail in the way a localized storm causes failure. A few substations tripped, some distribution lines down, repairs underway by morning. This was physical annihilation of the distribution network across the entire city. The utility, Mid-American Energy, had to call in mutual aid from 24 states. 2,500 additional line workers mobilized from across the country because the local and regional crews, workers who had spent their careers serving this grid, couldn't begin to address the scope of what had happened. Restoration took weeks. Some customers didn't get power back for over 3 weeks. During August, during a pandemic, 4 people died directly, and here is where the compound layer surfaces again. The same layering I traced through the 2012 event, but at a scale that dwarfs it. 10 million acres of Iowa cropland, corn and soybeans, the staple exports of the nation's agricultural heartland, were flattened. I spent time looking at the satellite imagery, and the before and after comparison is hard to process. Entire fields that had been standing at full height the morning of August 10th, green and vertical and weeks from harvest, were lying flat by afternoon, not bent, not leaning, flat, like a hand had pressed them into the earth. The crop insurance claims alone stretched into the billions. And the city itself, Cedar Rapids, Iowa's second largest city, about 135,000 people, was functionally uninhabitable for weeks. No power, no traffic signals, no functioning stoplights at any intersection in the city. Debris blocked every street, the tree canopy that had defined the city's neighborhoods for decades. The shade, the property values, the identity of the place was gone. Community volunteers and out-of-state crews worked in 100-degree heat to clear the wreckage, and some residents didn't have power restored for 3 weeks. During the hottest stretch of summer, during a pandemic, in a city that had already flooded catastrophically in 2008, the total damage assessment from NOAA came in at $11 billion, making it the costliest thunderstorm in United States history. Not the costliest tornado, not the costliest hurricane, the costliest thunderstorm. A single QLCS moving in a straight line in a single afternoon. And the part that locks back to the thesis, the NWS itself later acknowledged that if the destructive WEA tag had existed in August of 2020, it would have activated for this event. That is a retroactive admission. The agency confirming, after the fact, that the automated defense that would have sent an alert to every phone in the warning polygon wasn't built yet when the most expensive thunderstorm in American history arrived. The people of Cedar Rapids and Marshalltown, where the airport anemometer caught 99 miles per hour, and LeGrand, where it reached 106, learned what was happening when the trees started falling on their houses. Not from a siren, not from a phone alert, from the sound of their city being torn apart around them. 2 events, 2012 and 2020. 2 failure modes that are functionally identical. Warnings issued, urgency not communicated, population caught exposed. And the damage in both cases measured in billions. But the Iowa derecho revealed something the Washington derecho didn't, because Iowa sits in farm country, and what the wind did to 10 million acres of corn and soybean connects this investigation to a vulnerability that extends beyond any single city or any single grid. That compound layer, the grid, the crops, the heat, the cascading failures that multiply when the damage footprint exceeds what the response system can absorb, is where we're going next. But first, the mechanics. Because the physics of how the rear-inflow jet sustains and accelerates itself is the mechanism that explains why these storms don't weaken as they age. They get worse. Part 7, the physics inside the plow. And this is where the story takes a turn that most coverage completely misses. Because understanding the rear-inflow jet isn't just academic detail, it's the key to understanding why the warning window inverts as the storm matures. By the time a QLCS is most dangerous, the opportunity to warn has already passed. The mechanism itself explains the warning failure, and almost nobody covers it that way. I described the rear-inflow jet in Part 3 as a fire hose aimed sideways, cold, mid-level air descending behind the storm line and fanning out at the surface as straight-line wind. That's the basic picture, and it's accurate as far as it goes. But the deep mechanics reveal something more unsettling than a simple downdraft. They reveal a self-reinforcing feedback loop that Wiseman mapped out in his 1993 paper, that the Baymex Field campaign confirmed with direct airborne radar measurements in 2004, and that every major derecho since has validated with real-world damage data. The loop is the reason derechos don't fade as they cross state lines. They intensify, and once you see the feedback cycle, the entire warning problem clicks into focus. The cold air behind the storm line, rain-cooled, dense, heavy, spreads along the surface and undercuts the warm air ahead of it. That lifting is what keeps the thunderstorms alive along the leading edge. As those thunderstorms fire, they release enormous amounts of latent heat, the energy that was stored in the water vapor when it evaporated, now released as the vapor condenses into rain. That heat release alters the pressure field inside the storm complex, creating a pressure gradient that pulls mid-level air from behind the system toward the front. That pulled air is the rear-inflow jet. It descends at the apex of the bow echo and fans out along the surface as destructive straight-line wind. But here's the flywheel, and this is the part where the mechanism reveals why the warning problem gets worse, not better, as the storm matures. The stronger the rear-inflow jet, the stronger the gust front at the surface, the leading edge where cold outflow meets warm inflow. A stronger gust front produces more vigorous lifting of the warm air ahead of it. More vigorous lifting means more explosive convection, taller thunderstorms, heavier rain, more violent updrafts. More convection means more latent heat release. More heat release alters the pressure field inside the storm complex, steepening the gradient that pulls the rear inflow jet forward. And a steeper pressure gradient accelerates the jet. Each revolution of the cycle feeds the next. The storm doesn't weaken as it ages. It strengthens. It feeds on its own output. This is not a metaphor. This is fluid dynamics measured by instruments flown directly into the storm. Wiseman modeled the feedback cycle computationally, and then the Baymex field campaign, the Bow Echo and Mesoscale convective vortex experiment, led by Chris Davis and published in the Bulletin of the American Meteorological Society in 2004, went out and measured it. They flew research aircraft into mature Bow Echo environments over the Great Plains, deploying dropsondes and operating airborne Doppler radars to map the three-dimensional wind field inside these systems. The RIJ wind speeds they measured aloft matched Wiseman's theoretical predictions. The self-reinforcement was real, observable, and measurable. The storms were doing exactly what the physics said they would do, building internal momentum with every passing hour. And by the time the RIJ is fully descended and the Bow Echo is mature, the stage when surface winds are peaking at their absolute maximum destructive potential, the storm has been running for hours and is hundreds of miles from where it started. The communities now directly in the path had their best window to prepare, when the storm was weaker, smaller, and farther away, when the models were still uncertain and the SPC discussion was still hedging on the scope of the threat. By the time the system arrives at full strength, that window has closed. The storm's peak destructive phase and the target population's minimum preparation time coincide perfectly. That inversion isn't a failure of forecasting. It's built into the physics of how these systems work. Ron Przybylski at the NWS office in St. Louis, one of the people who has spent the most operational hours staring at QLCS events on radar, shift after shift, year after year, coined a term in 1995 for a specific hazard embedded in this system that nobody had systematically named. Along the leading edge of the Bow Echo, especially just north of the apex where the rear inflow jet is strongest, small-scale spin-ups form. They're tiny, 2 to 20 kilometers across, and they appear and vanish within minutes, sometimes within seconds. Przybylski called them mesovortices. They are not tornadoes in the classic sense. They don't form from a supercell's rotating updraft. They form from the shear zone along the gust front, where the wind changes speed and direction across a very short distance, and tiny pockets of rotation spin up like eddies behind a boulder in a river. Nolan Atkins at what was then Lyndon State College, now Northern Vermont University, published the definitive work on how mesovortices form in 2009 with his collaborator Saint Laurent. They identified two genesis mechanisms, one driven by the tilting of horizontal temperature gradients along the gust front into vertical rotation, and another driven by surges within the rear inflow jet and downdraft themselves, creating pockets of concentrated vorticity. These mesovortices can and do produce tornadoes. Brief, violent, almost impossible to detect on radar before they're already producing damage on the ground. The Perils Field Campaign, Propagation, Evolution, and Rotation in Linear Storms, conducted in 2022 and 2023 specifically to study QLCS tornadoes, deployed mobile Doppler radars, instrumented vehicles, and weather balloons into these environments. The field scientists drove into the path of active QLCS lines to try to observe mesovortex genesis from the inside, because the fixed NexRad radar network simply doesn't have the resolution to see these features forming until they're already producing surface damage. And this connects directly to the 49% detection number from Part 4. Those mesovortex tornadoes, the spin-ups that form with near zero lead time inside a broader wind field that is itself underworn, are the ones Anderson phrased data captured. Coin flip detection. Frequently zero or negative lead time. Embedded inside a 60-mile wide straight line wind threat that doesn't trigger tornado warnings or tornado sirens. The compound nature of the hazard, straight-line wind, plus embedded spin-up tornadoes that can't be reliably detected is what makes a mature QLCS qualitatively different from a supercell. A supercell gives you one concentrated threat that the system was designed to find. A QLCS gives you a 300-mile-wide threat field with invisible subthreats buried inside it like mines in a field. I don't know how to fix that from a detection standpoint, and I'm not sure anyone does yet. Warn on forecast. The next generation probabilistic warning framework under development at NSSL, the National Severe Storms Laboratory, is the most promising candidate. It aims to provide continuously updating probabilistic threat assessments rather than deterministic polygon warnings. But it's not operational. It exists in the research pipeline. And until it crosses into the operational world, the detection architecture remains optimized for a threat that rotates, deployed against an atmosphere that increasingly delivers one that doesn't. Part 8, the compound threat, when the grid falls everywhere at once. Here's a question that changed how I think about this entire investigation, and it came not from a meteorology paper, but from a power systems analysis. What happens when the mutual aid system that restores your electricity after a storm can't reach you because the storm took out everyone's electricity at once? When a tornado hits a community, and I've covered enough of these to understand the operational pattern, it devastates a narrow corridor. The damage is concentrated, intense, heartbreaking, but adjacent communities remain functional. The grid outside the damage path stays energized. The hospital 2 towns over still has power. The fire station in the next county still has communications. Mutual aid crews from neighboring utilities can stage at nearby intact substations, can access the area through roads that are mostly clear, can begin systematic restoration within hours because the problem is bounded. The system was designed for exactly this geometry: localized failure, intact surroundings, rapid mutual deployment, and it works. After a tornado, even a violent one, power restoration typically proceeds within days for most affected customers. A derecho inverts that geometry completely. A tornado is a sniper. It takes out one target with devastating precision. A derecho is carpet bombing. It takes down the grid across tens of thousands of square miles simultaneously. There is no adjacent intact grid to draw from. There is no nearby staging area with power and communications and clear roads. The hospital that was supposed to be the backup is also dark. The fire station that was supposed to coordinate the response is also running on generator. The mutual aid request doesn't go to the next county, it goes to the next time zone. After the Iowa 2020 derecho, Mid-American Energy brought in over 2,500 workers from 24 states. 24 states. That's not a mutual aid deployment. That's a national mobilization, and it took weeks to restore full service because the damage was so geographically vast that crews working from the edges inward had to rebuild, not repair, rebuild transmission and distribution infrastructure across an area larger than some European countries. And this connects to a vulnerability that Greg Dale at West Virginia University has been documenting for years through research funded by the Tree Fund. Trees are the leading cause of East Coast power outages. Everybody in utility forestry knows this. But Dahl's work surfaced a number that caught me off guard when I first saw it. 70 to 80% of tree-caused power outages come from trees that are outside the maintained right-of-way, not the trees directly under the power lines, the ones the utility trims on a cycle. The ones standing 30, 40, 60 feet away on private property, in public parks, along subdivision streets, trees that have never been assessed for structural integrity, never been maintained by the utility, never been considered a risk by the homeowner who waters them every spring, until a sustained 80-mile-per-hour wind topples them across the nearest wire. The eastern seaboard, from Virginia to Connecticut, runs through what arborists call the Green Tunnel. Dense, mature, deciduous hardwood canopy lining every road, every residential street, every transmission corridor. Oaks that predate the subdivisions they shade. Maples that were saplings when the power lines were strung. Tulip poplars that stand 80 feet tall with canopies spread 40 feet wide. It is beautiful. If you've driven the back roads of the Piedmont or the suburbs of Philadelphia or the Beltway corridor in summer, you know the Green Tunnel. You've driven through it with the windows down and the canopy closing overhead, and not once thought about what happens when sustained 80-mile-per-hour wind hits those trees for 30 uninterrupted minutes. That is a catastrophic vulnerability profile for exactly this type of event. Because wind loading on a tree isn't linear, the force scales roughly with the square of the wind speed, and it scales with the tree's sail area, the total leaf-bearing surface catching the wind. A gust to 60 that a healthy oak shrugs off becomes a sustained 80 that snaps it at the trunk. And when rain precedes the wind and loosens the root hold in saturated soil, which it often does in a QLCS, because the rain arrives on the leading edge before the strongest winds descend from behind, the tree doesn't snap. It uproots, root ball and all, across the wire, across the street, across the roof of the house next door. When 80-mile-per-hour winds sustain for 30 to 60 minutes across a swath 60 miles wide, every mature tree in that swath is a potential power line guillotine, and they all activate at once. If you want a single image for how this compounds at the grid level, consider the 2003 Northeast blackout. That cascade, which left 55 million people without power across the northeastern United States and Ontario, the largest blackout in North American history at that point, was triggered partly by a single tree contact near Cleveland. One tree touched one high-voltage transmission line. A protection relay that should have tripped failed to operate, and the cascade propagated through the interconnected eastern grid, one overloaded line tripping after another in a chain reaction, until a quarter of the continent went dark in roughly 9 seconds. One tree, one wire, 55 million people. A derecho crossing the I-95 corridor doesn't produce one tree contact. It produces thousands, hundreds of thousands, simultaneously across the most interconnected and load-critical section of the American power grid. The cascade risk is not theoretical. The 2003 blackout proved the grid is vulnerable to single-point failures. A derecho presents millions of simultaneous failure points across the same network. The mutual aid system that is supposed to restore service can't respond at normal speed because the mutual aid system is physically inside the damage path. The crews are driving through the same debris, sleeping in the same powerless hotels, fueling from the same offline gas stations as the residents they're trying to reach. But the grid is only the first compound layer. And if you followed this channel's previous work on compound events, the investigations into how cascading failures amplify beyond any single hazard, then you already know where this is heading. Because the same atmospheric setup that produces the wind also produces something else. Two something else's, actually. And when all three arrive together in the same 12-hour window, across the same geographic footprint, the emergency management system faces a triple threat that multiplies the number of people who need help while systematically dismantling the capacity to reach them. Part 9, the dual threat, wind and water. The atmospheric ingredients that build a derecho don't just build wind, they build rain. Extreme rain. And this is the piece where I have to connect two threads that are usually covered separately, but are mechanically inseparable. The same instability that generates the rear-inflow jet, the stored energy, the steep lapse rates, the explosive moisture content in the boundary layer, also drives extreme precipitation rates along the leading edge. The lifting along the gust front is violent and sustained, and the warm air being lifted is often saturated with precipitable water values exceeding 2 inches. A QLCS can drop 3, 4, 5 inches of rain in under an hour along its leading convective line, with the rain arriving just ahead of or simultaneous with the most damaging winds. The May 8, 2009 Super Derecho, the event I'll cover in Chunk 3, the one that traveled over 1,000 miles in 24 hours and built its own inland hurricane with a visible eye, produced flash flooding severe enough to close sections of the Kansas Turnpike. Cars were submerged on active highway lanes. Low water crossings on rural roads became impassable within minutes, and this happened simultaneously with sustained 70 to 90 mile-per-hour winds that were toppling trees and snapping utility poles across the same region. Think about what that dual threat looks like for a first responder. The wind has dropped trees across every road in the county, power lines are down and arcing across asphalt, and the water is rising. The routes you'd normally use to reach people who are trapped or injured are blocked by debris and flooded at the same time. Your mutual aid is overwhelmed because, as we just covered, the damage isn't in one neighborhood, it's across an area the size of a state. You can't drive to the calls because the trees are blocking the roads. You can't detour because the low spots on the detour routes are under 3 feet of water. And the calls keep coming because the storm is still producing damage as it moves east at 60 miles per hour, outrunning your response, adding new victims to the queue faster than you can reach the ones already waiting. That scenario isn't hypothetical. It played out across southern Illinois and Kentucky during the 2009 super derecho, where emergency managers reported that road access to affected communities was completely cut off for hours by the combination of tree debris and flash flooding. It played out on a smaller scale during the June 2020 Pennsylvania derecho that killed 4 people and left nearly 1 million customers without power across the mid-Atlantic, where first responders in multiple counties reported that neither primary nor secondary road routes were passable in the immediate aftermath. But the third layer, and this is the one that haunts me, the one I keep circling back to, is the heat. The heat killed more people in 2012 than the wind itself. And this is not a coincidence. The atmospheric feature that fuels the most powerful derechos has a name that forecasters track on the SPC mesoanalysis page. And once you understand it, the compound nature of the threat becomes inescapable. It's called the elevated mixed layer, a tongue of hot, dry air sitting in the mid-levels of the atmosphere, typically originating over the elevated terrain of the desert southwest or northern Mexico, slides eastward over the moist surface air of the Great Plains and the Mississippi Valley. Picture a loaded gun sitting over the landscape, hot, dry air at 15,000 feet, perched on top of a swamp at the surface. The temperature drops from that hot, dry layer to the cooler, saturated air above it at an incredibly steep rate, steep enough that any parcel of surface air that gets lifted through the cap explodes upward with enormous energy. The lapse rates become extreme. The stored energy available for convection, the compressed spring, reaches 2,000, 3,000, 4,000, 5,000 joules per kilogram. Those numbers are the fuel state for the biggest derechos in the modern record. And here's the mechanical link that makes this a true compound event, not just 2 bad things happening at the same time. The elevated mixed layer that fuels the derecho is the heat wave. The same hot, dry, mid-level air that creates the steep lapse rates that power the rear-inflow jet also produces the oppressive surface temperatures that kill people when the power goes out. It's one hand resting on a console of levers. When that hand pushes down, the wind lever and the heat lever move together, because they're connected to the same atmospheric mechanism. You cannot separate them. The conditions that maximize the derecho threat are the same conditions that maximize the heat threat that follows it. In 2012, 13 people died from the wind. 34 died from the heat that followed the grid collapse, more than double. And this asymmetry reveals something important about how the compound threat is structured. The wind is the visible event, the one that makes the news footage, the one that gets the NWS service assessment, and the NOAA damage estimate. The heat is the silent partner. It doesn't make the front page. It doesn't have a damage survey team. It doesn't get $1 billion price tag. But it killed nearly 3 times as many people as the storm itself. And it killed them slowly, over days, in overheated apartments, in homes without fans, in neighborhoods where the power company couldn't reach because the tree debris hadn't been cleared, because the grid damage was too widespread, because the storm wasn't a tornado cutting a narrow path. It was a derecho, and the damage was everywhere. Previous orbital view investigations have documented how compound events, where the underlying mechanism links multiple hazard layers, produce consequences that exceed the sum of the individual threats. The derecho compound is among the most severe examples in the continental United States because all 3 layers, wind, flood, and heat, share a single atmospheric driver and strike simultaneously across the same geographic footprint. So the storms are compound, wind, flood, and heat, delivered by a shared mechanism that cannot be decoupled. The grid is vulnerable, not to localized damage, but to simultaneous wide area collapse that overwhelms the mutual aid system designed for localized failure. The warning architecture has a structural blind spot for the wind that does the most widespread damage. And the question that should follow, the one that determines whether this is a bad luck story or a systemic crisis that's actively getting worse, is whether the frequency and geographic footprint of these events are changing. There is an answer. It comes from Andreas Prehn at NCAR, and the number, when I first encountered it in his 2023 paper in Nature Climate Change, stopped me cold. Part 10, the number from NCAR, nobody is talking about. There is a paper that should be front page news and isn't. It was published in 2023 in Nature Climate Change, one of the highest impact journals in the climate sciences, and the lead author is Andreas Prehn at the National Center for Atmospheric Research in Boulder, Colorado. What Prehn and his team did was something nobody had systematically attempted before. They tracked the geographic footprint of damaging straight-line wind events across the United States over a 40-year observational window. Not the intensity of individual storms, not peak gust speed, not the EF rating of associated tornadoes. The footprint, the total geographic area each event covered with wind damage. And you can pull up this paper yourself. It's in Nature Climate Change, 2023, Prehn et al. The number that came out of that analysis is 4.8, plus or minus 1.2. That's a fold increase. The geographic extent affected by damaging straight-line winds grew by nearly a factor of 5 over 4 decades of observation. I sat with that number for a long time before I wrote this section, because it's the kind of finding that reframes an entire threat landscape if you let it. And I wasn't sure, at first, that I was reading it correctly. A 5-fold increase sounded too large, too dramatic, too clean. So I went back to the methodology, the error bars, the controls for reporting bias, and radar network expansion. Prehn's team accounted for the known increase in severe weather reports driven by population growth and spotter network expansion. They accounted for the improvement in radar coverage. The signal survived every correction they applied. The expansion is real. I sat with that number for a while before I wrote this section, because it's the kind of finding that reframes an entire threat landscape. The storms aren't just getting stronger, although some evidence suggests they are in certain environments. They're getting wider. The area of ground each event covers with damaging wind is expanding, and the expansion rate, 13% per degree Celsius, means this isn't a slow generational drift. It's happening on a timescale that matters for the people living in the expansion zone right now. Picture a searchlight sweeping across a room. The beam itself hasn't fundamentally changed in brightness or intensity, but the arc of the sweep has nearly quintupled. The beam covers 5 times more floor space with each pass, and the room it's sweeping through, the I-95 corridor, the Northeast megalopolis, the stretch from Washington through Baltimore, through Philadelphia, through New York to Boston, houses 53 million people on less than 2% of the national land area. That's roughly 15% of the entire U.S. population packed into a corridor that the data says is experiencing expanding straight-line wind exposure. The searchlight is getting wider, and the densest cluster of people in America is sitting in its expanding arc. Prehn's analysis quantified the rate of expansion, roughly 13% per degree Celsius of warming. That means every degree the planet warms, the footprint of these events grows by 13%. And we are not talking about a distant future scenario. The warming that has already occurred, the roughly 1.2 degrees Celsius above pre-industrial, that the planet has already locked in, has already driven most of the expansion Prehn measured. The 4.8-fold increase isn't a projection, it's a measurement of what has already happened. Brian Squitieri and his co-authors took the question a step further in the Bulletin of the American Meteorological Society, also in 2023. They ran what climate scientists call pseudo-global warming simulations, taking the observed atmospheric conditions of the 2020 Iowa derecho and replaying the event inside a model atmosphere warmed to end-of-century levels. Same storm dynamics, hotter planet. Their conclusion, a future analog of the 2020 derecho, may not necessarily have more intense winds, but could possibly impact a geographical area 50 to 100% larger. Read those numbers carefully. The winds might not get faster. But the damage swath could double in area. An event like the 2020 derecho, which already covered 90,000 square miles, could cover 135 to 180,000 square miles in a warmer atmosphere. That is not a rounding error. That is the difference between a disaster that overwhelms Iowa and a disaster that overwhelms the entire eastern third of the country. And I need to be careful with my own framing here, because the attribution science for individual derechos is still an active research frontier. I'm not going to pretend this is more settled than it is. Global climate models don't cleanly resolve the mesoscale environments that produce QLCS events. The grid spacing in most general circulation models is too coarse to capture the convective dynamics that drive a bow echo. The projections rely on downscaling methods and pseudo-global warming frameworks that carry real and acknowledged uncertainty. Squitieri himself uses the word possibly. Preen's observational trend is more robust. It's based on 40 years of actual measured events, not model output. But even Preen's work requires careful accounting for changes in reporting practices, radar coverage density, and population distribution in affected areas over those 4 decades. The honest statement is, the signal is strong, the direction is unambiguous, the expansion is real, and the precise magnitude is still being refined. That's different from certainty, but the trajectory, expansion, toward the population driven by warming is not in dispute among the researchers publishing in this space. Walker Ashley and Alex Haberle at Northern Illinois and LSU, along with Victor Gensini, have published complementary work examining how the environments favorable for severe convection are shifting geographically under warming. Their findings are consistent with Preen's. The conditions that produce the most dangerous thunderstorm environments are expanding eastward and northward, toward higher population densities and toward infrastructure that was designed for a different climate. So the footprint is growing. The population in the expansion zone is dense. Over 64 million people live within 50 miles of the I-95 interstate alone, per census data from the year 2000. The Northeast megalopolis, from Washington to Boston, houses 53 million people on less than 2% of the national land area. The density in that corridor runs between 900 and 1,200 people per square mile. And the physical infrastructure those tens of millions of people depend on, the buildings, the grid, the roads, the emergency response systems, was never designed for what a mature QLCS delivers. Not because anyone made a mistake, because the building codes were written for a different threat. Part 11, the code that doesn't cover this, the document that governs how buildings in the United States are designed to resist wind, is called ASCE 7, published by the American Society of Civil Engineers and referenced by the International Building Code that most jurisdictions adopt. It is a serious, meticulously engineered standard, and it has a gap that maps almost perfectly onto the thesis of this investigation. Interior mid-Atlantic structures, Pennsylvania, West Virginia, Virginia, the belt of geography that the I-95 corridor passes through between Washington and New York, are designed under ASCE 7's risk category 2 to withstand roughly 110 to 115 miles per hour. Sounds adequate? Sounds like it covers a derecho? But that number deserves a closer look, because what it actually specifies is a 3-second gust, measured at 33 feet above the ground in open terrain, with a return period of roughly 700 years. It is a statistical snapshot, the peak instantaneous gust. The structure is engineered to survive once in 7 centuries of exposure. It is not a sustained wind rating. It does not describe a loading condition where 80 to 100 mile per hour winds press against the building envelope continuously for 30 to 60 minutes, which is what a mature derecho delivers. The distinction is not academic, and this is one of the areas where I had to educate myself during this investigation, because structural engineering isn't my primary domain, but the engineers I consulted were emphatic about this point. The difference between impulse loading and sustained loading changes the failure mode of buildings. A 3-second gust at 110 miles per hour is an impulse, a sharp, brief spike of pressure that the structure absorbs and recovers from, like a punch that rocks you back on your heels but doesn't knock you down. A 30-minute wind field at 85 miles per hour is sustained loading across a broad area. The pressure doesn't relent, it presses. Materials fatigue, fasteners work loose. Connections that survive the first minute of loading begin to fail by the 15th. Roofing peels incrementally, the edge lifts, then the next panel, then the next. Cladding separates from building facades as the screws holding it fail one by one. Older masonry walls develop cracks that propagate under continued pressure. And critically, this is the infrastructure point. The failures don't happen to one building at a time. They happen across an entire metro simultaneously, because the wind field is 60 miles wide and the wind doesn't let up for half an hour or more. ASCE 7 also includes an explicit statement that caught my attention during this research. The standard does not design for direct tornado strikes. The reasoning is probabilistic. The probability of a specific site being struck by a tornado is extremely low, so designing every building for tornado-level winds would be economically impractical. Fair enough. But the implicit assumption behind that exclusion is that the only wind event capable of exceeding the design basis is a tornado, a rare, narrow, localized phenomenon. A derecho delivers wind speeds that can match an EF2 tornado across a swath 60 miles wide. It's not a tornado. It doesn't fall under the tornado exclusion, but it also wasn't the event the design basis was calibrated against. And in 2022, the most recent revision, ASCE 7-22, actually moved the 130 mile per hour wind speed contour off the North Atlantic coast, effectively removing portions of the Northeast from the windborne debris region designation. The standard relaxed, not tightened, the wind requirements for the region that the climate data says is experiencing expanding straight-line wind exposure. If you want a visual for what happens when these design assumptions meet a real derecho in an urban environment, look at what happened in Houston. In May of 2024, a fast-moving QLCS crossed the Houston metro area with measured wind gusts exceeding 100 miles per hour in some locations. The storm struck the downtown core during a weekday when the high-rise commercial district was fully occupied. 2,500 skyscraper windows, glass curtain wall systems, the modern cladding that defines the American commercial skyline from Houston to Manhattan were blown out in a single afternoon. Glass rained onto downtown streets from dozens of stories up. Cars were crushed. Sidewalks became impassable. 8 people died in Harris County alone. The power outage affected over 1 million customers and lasted, for some, multiple weeks into the Texas summer heat. The damage wasn't from a tornado. No tornado struck downtown Houston that day. It was from straight-line wind, the same kind of wind that the QLCS mechanism delivers, sustained at speeds and durations that the glass curtain wall systems were not engineered to survive. And Houston is a city that understands hurricanes, that has building codes shaped by hurricane exposure, that has emergency management infrastructure refined by decades of tropical cyclone threats. The derecho bypassed all of that experience because it arrived from the wrong direction, at the wrong speed, with the wrong warning product. The building code is a promise. It says, your structure can handle this. But the promise was written for a tornado that touches down for seconds and moves on, and a hurricane that gives you 3 days of tracking data and cultural preparation and protocols refined over decades. The boarding of windows, the stocking of supplies, the voluntary and mandatory evacuations that coastal communities have drilled into institutional muscle memory. A derecho rewrites both assumptions at once. It delivers hurricane force winds with tornado-level warning time, and it does it across the width of a state. The code doesn't account for it. The emergency management plans don't account for it. And the public has no cultural protocol for it. Consider the asymmetry. If a Category 3 hurricane is approaching the coast of Virginia, every person in the warning area knows days in advance. The governor declares a state of emergency. Schools close. Hardware stores sell out of plywood. Evacuation routes activate. The cultural machinery of hurricane preparedness, built over generations of Gulf and Atlantic coast experience, engages automatically. People know what a hurricane means. They know what to do. If a derecho is approaching the same geography from the west, bearing winds of identical speed and potentially wider destructive reach, The population has no equivalent framework, no derecho season in their mental calendar, no plywood protocol, no evacuation instinct. The word itself, derecho, was unknown to most Americans until 2012. The warning, if it comes at all, arrives as a severe thunderstorm warning on a weather app that most people don't check between dinner and bedtime. The gap between the threat and the cultural preparation for the threat is total. The answer to what happens when a QLCS arrives at a population center with no preparation, no cultural framework, no protective architecture matched to the hazard, no warning infrastructure calibrated for the actual threat, is not theoretical. It has been demonstrated repeatedly, but the most extreme demonstration, the one that pushed the QLCS phenomenon to its absolute upper boundary of physical possibility, happened on May 8th of 2009. And the event that unfolded over the next 24 hours is, even by derecho standards, genuinely difficult to believe. Part 12, the super derecho and the inland hurricane southeastern Kansas. Late afternoon on May 8th, 2009. A cluster of severe thunderstorms that had been firing intermittently across the southern plains began organizing along a cold front into something the SPC was already flagging as potentially significant. The initial convective mode was messy, multiple cells, scattered, no clear dominant structure that would normally trigger a high-confidence watch. But as the system moved into southern Missouri after dark, something changed. The individual cells began merging. The radar presentation at the NWS office in Springfield, and later at NWS Paducah, as the system crossed into their county warning area, showed the line tightening, organizing, developing the characteristic bow shape that operational forecasters recognize as the signature of a maturing QLCS. By the time it reached southern Illinois, the bow echo was pronounced, the rear inflow jet was established, and the system was accelerating, and then it just kept going. Over 1,000 miles in 24 hours. 15 hours and 28 minutes of continuous severe weather production, the longest duration of any documented derecho in the modern observational record. From southeastern Kansas through southern Missouri, across southern Illinois, into western Kentucky, and up into the Appalachians of West Virginia. The system spawned 39 tornadoes along the way, 2 of them rated EF3, and produced straight-line wind gusts measured at 106 miles per hour at the southern Illinois airport, where a backup anemometer captured the reading after the primary wind instrument was destroyed by the storm itself. Damage surveys in multiple counties across southern Illinois and western Kentucky estimated winds reaching 120 miles per hour in the hardest hit areas. 6 people died across the multi-state path. But the part of the 2009 event that still stops researchers in their tracks, the feature that earned this system its own classification, is what happened to the system's internal structure as it matured. Late in its life cycle, as the QLCS crossed into western Kentucky, the system generated a feature that has no business appearing inside a thunderstorm complex. A mesoscale convective vortex, a large-scale rotation within the broader storm system, developed a warm core. The mid-level circulation tightened, and on radar and on satellite imagery, the structure began to resemble something unmistakable, a tropical cyclone, an eye, a clear, calm center surrounded by a ring of the most intense convection and the highest wind speeds. Sustained surface winds of 70 to 90 miles per hour, tropical storm to Category 1 hurricane equivalent, wrapped around this feature for hours as it tracked across Kentucky. Meteorologists labeled it an inland hurricane, not as a metaphor, not as a dramatization for the evening news, as a physically accurate description of the observed wind field and structure. I need you to hold those 2 words together because they shouldn't fit. Hurricanes are ocean creatures. They need warm water, sea surface temperatures above about 78 degrees Fahrenheit to sustain the latent heat flux that powers their wind field. They form over tropical oceans and weaken rapidly once they move inland, starved of their energy source. An inland hurricane inverts that entire paradigm. This system had built its own tropical-like architecture, entirely from continental ingredients. No ocean, no warm sea surface temperatures, No tropical disturbance or easterly wave as a precursor. Just 15 hours of uninterrupted convective energy production, fueled by an atmosphere so overloaded with instability and boundary layer moisture that the storm complex organized itself into a coherent vortex with a warm core that genuinely mimicked the thermodynamic structure of a landfalling hurricane. Except it never made landfall. It was born on land. It lived on land. And it died on land, having crossed 5 states and left a damage path over 1,000 miles long. The 2009 event prompted the creation of a new formal classification. In 2010, the meteorological community proposed the term super derecho for events that exceed standard derecho criteria in both duration and structural complexity, systems that persist for more than 12 hours, span more than 1,000 miles, and develop internal organizational features beyond a simple bow echo. The SPC's own warning language during the event reflected the category confusion the system experienced in real time. They issued PDS severe thunderstorm watches, alongside tornado watches that mentioned, in the same watch discussion, winds in excess of 105 miles per hour. The language was blurring. Severe thunderstorm warning language, tornado watch language, hurricane scale wind references. All in the same product for the same event, because the existing warning categories hadn't been designed to hold what the atmosphere was producing. And this event proves the upper bound of what the atmosphere can assemble through the QLCS mechanism. Not a hypothesis, not a model run. An observed, documented, instrumentally verified event. The capacity exists. The mechanism exists. And the warning system, the sirens, the phone alerts, the cultural urgency was never built for it. Every time an event this extreme happens, every time the damage looks like a war zone, and the official explanation is, it was a thunderstorm, a predictable set of claims starts circulating online. You've seen them. HARP, weather modification, directed energy weapons, government weather control. And the people making those claims deserve an actual answer, not a dismissal, but an answer grounded in specific physics. Part 13, the claims and the physics. The impulse behind conspiracy theories about extreme weather is not irrational. When a storm that nobody warned you about flattens your neighborhood and the explanation you're given is, it was a severe thunderstorm. The mismatch between the destruction you see and the warning you didn't receive creates a cognitive gap. People look for explanations that match the scale of what they experienced. The atmosphere is complicated, doesn't feel sufficient when you're standing in front of a house that looks like it was bombed. So people reach for explanations that feel proportionate. Secret technology, government intervention, weather weapons. The emotional logic is understandable even when the physics is wrong. So let me address them directly, because dismissing these claims without engaging the physics doesn't serve anyone. HARP, the High Frequency Active Auroral Research Program, now operated by the University of Alaska Fairbanks, previously by the U.S. Air Force and Navy, is the most commonly cited candidate for weather modification claims. And I understand why. It sounds plausible at first glance. A large antenna array in remote Alaska, funded by the military, transmitting high-power radio waves into the atmosphere. The facility transmits electromagnetic energy into the ionosphere, the layer of the atmosphere between about 30 and 600 miles above the Earth's surface, to study how the ionosphere responds to controlled energy input. It does real science. Published, peer-reviewed, unclassified science available to anyone with a journal subscription. But its maximum radiated power is 3.6 megawatts. And that number, by itself, tells you everything you need to know about whether HARP can influence a thunderstorm. Umran Inan, a professor of electrical engineering at Stanford, who has published extensively on ionospheric physics and the interaction between electromagnetic waves and the upper atmosphere, characterized it this way. HARP's radiated power is minuscule compared with the power of a lightning flash. A single lightning bolt releases roughly 1 billion watts instantaneously, a gigawatt for a fraction of a second. HARP produces 3.6 million watts, sustained. It would take roughly 300 HARP facilities, operating simultaneously to match the instantaneous power output of one lightning bolt, and a mature derecho contains thousands of lightning flashes per hour, while simultaneously converting atmospheric instability into kinetic wind energy at rates equivalent to multiple nuclear detonations per hour through latent heat conversion alone. The scale mismatch isn't close. It's not even in the same universe. You cannot steer a derecho with HAARP any more than you can redirect the Mississippi River with a garden hose. The energy is not there. The mechanism is not there. And the ionosphere, where HAARP operates, 30 miles up at minimum, is physically disconnected from the tropospheric processes below 10 miles that produce thunderstorms, derechos, and all the surface weather humans experience. NOAA has addressed this directly on its climate.gov fact-check page. No technology exists that can create, destroy, modify, strengthen, or steer severe storms. That statement isn't hedged, it's categorical. But here is where the conspiracy framing gets unexpectedly interesting, at the one alternative that has a genuine scientific basis. Cloud seeding is real. It exists. It's operational right now, used by water utilities in the western United States, by agricultural interests, by several national governments, including China and the United Arab Emirates. The mechanism is straightforward. Silver iodide particles are introduced into clouds to serve as ice nuclei, promoting the growth of ice crystals that fall as precipitation. It works modestly. Published studies show it can increase precipitation in targeted areas by roughly 10 to 15% under favorable conditions. But cloud seeding cannot create a thunderstorm. It cannot create a derecho. It cannot steer a mesoscale convective system or determine where a bow echo forms or which communities the rear inflow jet strikes. The energy involved in a QLCS, the latent heat release from billions of tons of condensing water vapor, the kinetic energy of a rear inflow jet moving at 100 knots across a front 300 miles wide, the pressure gradients driving a bow echo 700 miles across the continent is self-generated by the atmosphere through thermodynamic processes operating at scales that dwarf any human technology by many orders of magnitude. Cloud seeding is the one real thing in the conspiracy drawer, and it's a water pistol next to a fire hydrant. The real human fingerprint on these events is documented, peer-reviewed, but I have to say this plainly, more alarming than the fabricated one. It doesn't require secret installations in Alaska or classified weapon systems. It requires a thermometer, a rain gauge, 40 years of data, and a warming atmosphere. It's the fingerprint that Prane measured, a nearly 5-fold expansion of straight-line wind event footprints, driven by a planet that is warmer, wetter in the boundary layer, and generating steeper lapse rates that load more energy into the storms the atmosphere builds every summer. It's the fingerprint Squitieri projected forward, a future derecho covering 50 to 100% more area than the one that already set the record for the costliest thunderstorm in American history. The conspiracy explanation is wrong. The actual explanation, that human-caused warming is measurably expanding the geographic reach of the most destructive and least warned wind threat on the eastern seaboard, is simpler, better supported, and more consequential than anything HAARP could produce if you gave it 1,000 times more power. And that brings us to the question this entire investigation has been building toward. The warning gap is real. The detection failure is documented. The compound threat multiplies the consequences. The climate signal is expanding the footprint. 3 case studies spanning 14 years, all exhibiting the same fundamental failure mode: warnings issued, urgency not communicated, population caught exposed. How do you hold all of that at once? The answer isn't simple, it isn't comfortable, and it splits into 3 possible readings of the same evidence, each one defensible, each one carrying a different set of costs if it turns out to be wrong. Part 14, the reassuring interpretation. Before I lay out the 3 readings of this evidence, I want to do something that matters more than any single data point in this investigation. I want to be fair. The most reassuring interpretation of everything I've shown you is not a straw man. It is not a naive reading. It is held by serious people who work inside the system, who have spent their careers trying to protect the public and who have access to more operational data than I do. Dismissing it would be dishonest, and dishonesty is the one thing I've promised you this channel won't deliver. Here is the reassuring case, presented as completely as I can. The NWS Service Assessment for the 2012 derecho, the same assessment I've quoted at length, contained a finding I haven't mentioned yet, and it's important. The assessment concluded that the NWS offices involved generally did an excellent job in their warning performance. The average severe thunderstorm warning lead time out of WFO Sterling was 37 minutes. That is strong by any operational standard. The forecasters identified the threat correctly, communicated it through the appropriate warning product, and did so with lead times that exceeded the national average for severe thunderstorm warnings. The system, by its own internal metrics, performed well, and the system has improved since 2012, meaningfully, not cosmetically. The destructive severe thunderstorm warning tag, implemented on August 2nd of 2021, now triggers a wireless emergency alert for the most extreme events. That is a real operational upgrade to the warning pipeline, the first time the system has automated a phone-level alert for non-tornadic wind. It means the 80-mile-per-hour plus events, the ones that produce the most catastrophic damage, the ones that match or exceed EF1 tornado intensity, now reach your phone the same way a tornado warning does. That matters. It didn't exist 14 years ago. It didn't exist 5 years ago. And the people who designed it, Greg Skoor and the Hazard Simplification team, did serious work under real institutional constraints to get it through the development pipeline and into operational deployment. The modeling capability has transformed. The HRRR, the High Resolution Rapid Refresh, the only model that correctly depicted the 2012 derecho and was ignored because it was experimental, is now fully operational, runs every hour, and is regarded across the international forecasting community as one of the best short-range convective prediction tools on the planet. It can see QLCS formation potential 12 to 18 hours out, with a skill level that would have been unimaginable when the 2012 derecho caught the NAM and GFS flat-footed. Convection allowing model ensembles, multiple HRRR class models, run with slightly different initial conditions to produce a range of possible outcomes, are giving forecasters probabilistic guidance on QLCS development that simply didn't exist a decade ago. And the SPC has revised its formal derecho definition as of 2025, working with Squitieri and others to improve classification and communication within the forecasting community. Warn on Forecast, the probabilistic warning framework being developed at the National Severe Storms Laboratory, represents perhaps the most ambitious rethinking of the warning paradigm since the creation of the polygon-based warning system itself. Instead of issuing a single deterministic warning, a tornado is approaching your area, Warn on Forecast aims to provide continuously updating probability fields. There is a 40% chance of damaging wind at your location in the next 30 minutes. It would fundamentally change how the public receives and processes threat information. It's not operational yet, but the science is sound, the prototyping is active, and the path from research to operations is visible, if not imminent. And there is a base rate argument that deserves honest weight. I'm not going to pretend this consideration doesn't matter. For any single location, your neighborhood, your city, the block where you park your car, a major derecho is rare. Cedar Rapids had never experienced one in living memory before 2020. Washington, D.C. hadn't seen one in decades before 2012. Pittsburgh International's 71 MF gust in 2025 was only the third strongest in the station's entire record. The probability that your specific address is struck by a mature QLCS derecho in any given year is low, genuinely low, not artificially reassuringly low. The risk is real, but distributed across a vast area and a long time horizon, and the insurance industry, which is ruthlessly effective at pricing tail risk because money depends on getting it right, has not restructured its entire residential wind risk portfolio around derechos. This interpretation says the system took the hit. It studied the damage. It patched the hull, not perfectly, but meaningfully. The tools are better. The warnings are improving. The base rate is low enough that the residual risk, while real, is manageable within the existing framework. That interpretation is not wrong. It is fair. It accounts for real progress made by real people doing difficult work under institutional constraints. But it also requires you to accept a set of assumptions about the pace of improvement, and the intermediate interpretation, the one the published research most directly supports, challenges those assumptions with specific numbers that are difficult to dismiss. Part 15. The intermediate interpretation. The intermediate case starts where the reassuring case ends, with the reforms, and asks the harder question, are the reforms fast enough? And are they reaching the right people? The destructive tag is real progress. It is also, by the NWS's own data, triggered by only 10% of severe thunderstorms nationwide in any given year. That's a national average, and averages conceal enormous geographic variation. In the heart of Tornado Alley, where severe thunderstorm wind gusts routinely exceed 80 miles per hour during spring and summer, the destructive tag fires more frequently. Forecasters and the public in Oklahoma and Kansas have more exposure to the product. In the Northeast, where the I-95 corridor runs, where the population density is highest, where the derecho threat is expanding, one operational meteorologist at WHSV in the Shenandoah Valley estimated the destructive tag activates in his specific forecast area maybe once every 5 to 7 years. That's the regional reality. The tool exists nationally. The experience with the tool is concentrated in the regions that already have the strongest severe weather culture, the regions that need it most, the densely populated eastern metros, where straight-line wind literacy is lowest, encounter it least. And for the vast majority of severe thunderstorm events, including events with sustained 75-mile-per-hour winds that can kill, that can collapse mobile homes and manufactured housing, that can topple 80-foot trees onto occupied vehicles, that can launch construction debris through residential windows, the destructive threshold is not reached. The automated phone alert doesn't fire. The gap between the tornado warning's automatic, unavoidable urgency and the severe thunderstorm warning's passive, check. Your app, if you think of it notification, remains intact for 9 out of 10 severe storms. And if that storm happens to be a QLCS, a wall of wind 60 miles wide, moving at 60 miles per hour, with embedded mesovortices that the radar catches half the time, the 9 out of 10 figure isn't a statistical curiosity, it's a survival-relevant detail. The QLCS tornado detection problem has not been solved. Anderson Frey's 49% probability of detection is a published number from 2016, and nothing in the intervening decade has fundamentally altered the physics that makes QLCS tornadoes hard to detect. The mesovortices still form at scales below the NEXRAD radar's effective resolution, 2 to 20 kilometers, appearing and vanishing in minutes. The algorithms are improving at the margins. Machine learning approaches to radar interpretation are being tested. Dual polarization data is being incorporated into detection workflows. But the core physical constraint remains. QLCS tornadoes form at spatial and temporal scales that the fixed WSR network wasn't designed to resolve. Perils generated valuable field data, and that data will eventually feed improved detection methods. Eventually, the gap between field campaign data collected and improved warning issued to your phone in real time is measured in years to decades, not months. Meanwhile, warn on forecast, the most promising systemic reform on the horizon, remains under development. It is not operational. It is being prototyped and tested in research environments. And the gap between research demonstration and operational deployment in the NWS system historically spans 5 to 15 years, depending on institutional priorities, congressional funding cycles, technology transfer logistics, and the speed at which 122 forecast offices across the country can be trained, equipped, and culturally adapted to a new warning paradigm. The HRRR itself, a single model, not a systemic framework change, took nearly a decade to go from experimental to operational. Warn on forecast is more ambitious by an order of magnitude. It's not just a new model, it's a new philosophy of warning. And philosophies move through institutions slowly. And there is a constraint that nobody in the NWS discusses on the record, but that shapes every decision about WEA policy: alert fatigue. The public's willingness to respond to phone alerts is a finite resource, and the NWS knows it. In 2019, the agency scaled back flash flood wireless emergency alerts to only the considerable and catastrophic tiers, because the sheer volume of flash flood alerts was causing documented fatigue, people ignoring them, silencing their phones, treating the alarm tone as background noise. The same institutional pressure acts as a real and legitimate brake on expanding WEA triggers for severe thunderstorm warnings. Lowering the destructive threshold from 80 to, say, 70 miles per hour would capture many more dangerous events, but it would also triple or quadruple the number of phone alerts the public receives for non-tornadic wind. More alerts risks more fatigue. More fatigue risks more people who, when the 120 mile per hour derecho arrives, have already trained themselves to ignore the sound their phone makes. The NWS is caught in a genuine dilemma, a trade-off between coverage and credibility, and reasonable people can disagree about where the right balance sits. But the climate signal isn't waiting for the balance to be struck. Preen's data shows a 5-fold footprint expansion over 40 years, roughly 13% per degree Celsius, and the warming that drove it isn't slowing down. The hazard is growing on a timescale of years. The institutional reforms are moving on a timescale of decades. The system is patching a roof while the rain is getting heavier. The patches are real. The rain is faster. And the question this interpretation forces is whether the institutional machinery of the United States can close the gap before the atmosphere delivers an event that exploits it at full scale. A mature QLCS crossing the DC, Philadelphia, New York corridor during peak heating season with 53 million people in the path, and a warning system that may or may not activate in time. This interpretation says the gap exists, the NWS knows it exists, the reforms are genuine but insufficient in scope and pace, and the question is whether the institutional machinery can close the gap before the next major QLCS crosses the I-95 corridor with 53 million people in its path. The published evidence suggests the answer is probably not in time. Part 16, the concerning interpretation. The most concerning reading of this evidence does not require speculation. It requires only extrapolation from published data, and it's the interpretation that keeps the researchers who study these systems awake in ways they don't always say publicly. The argument is structural. The warning gap is not a policy flaw that better policy can fix. It is an architecture mismatch between the nature of the threat and the design of the system. The entire warning infrastructure, the sirens, the WEA triggers, the cultural training, the public's mental model of what a dangerous storm looks like was built around rotation, around the tornado. The tornado is the threat the system was optimized for, and the optimization was rational given the state of knowledge when the system was designed. But the most widespread and economically destructive wind threat the atmosphere delivers to the eastern seaboard is not a tornado. It's a QLCS. It doesn't rotate, it doesn't trigger the automated defenses. And the detection algorithms that feed the warning pipeline, the mesocyclone signatures, the tornado vortex signature, the velocity couplet algorithms are hunting for a feature the primary threat doesn't produce. QLCS tornado detection remains below 50%. A coin flip. Lead times for the tornadoes that are detected average 12 minutes and frequently hit zero. The straight line wins, the primary damage mechanism, the thing that costs $11 billion and strips a city of its tree canopy in under an hour, don't trigger tornado warnings at all because they aren't tornadoes. The destructive tag covers 10% of severe storms and was implemented 5 years ago. The building code doesn't distinguish between a 3-second gust and a 30-minute siege. And tens of millions of people on the I-95 corridor have no cultural framework for the word derecho, no hurricane season equivalent, no preparation protocol, no instinct to shelter that matches the instinct triggered by the word tornado. And the climate data says the footprint is expanding. Preen, 5-fold in 40 years. Squitieri, 50 to 100% larger by end of century. The expansion is directionally toward the population, not away from it. The threat is growing into the gap, and the gap is closing slower than the threat is growing. The next major QLCS to cross the I-95 corridor, to cross the DC Metro, the Baltimore-Washington Parkway, the Philadelphia suburbs, the New Jersey Turnpike, the approach to New York City in a single evening will encounter a population of 53 million people who have no cultural vocabulary for what is happening to them. A warning system that may or may not send an alert to their phones, depending on whether the measured wind speed crosses the 80-mile-per-hour threshold that triggers the destructive tag, a threshold that sits above the wind speed capable of killing people, collapsing mobile homes, and toppling trees onto occupied vehicles. Building codes calibrated for a 3-second gust in a 700-year return period, not a 30-minute siege. A tree canopy, the green tunnel of the eastern seaboard, that will turn into a mass casualty mechanism at sustained winds above 70 miles per hour, as every untrimmed oak and maple within striking distance of a power line, a road, or a rooftop becomes a projectile, and a power grid that will fail simultaneously across thousands of square miles, overwhelming the mutual aid system, collapsing emergency communications, and leaving medically vulnerable populations without cooling during the heat wave that, as we've established, is mechanically coupled to the same atmospheric setup that produces the wind. The atmosphere doesn't care what the system was built for. The atmosphere doesn't care about the 80-mile-per-hour threshold. The atmosphere doesn't care that the word derecho is unfamiliar, that the siren is culturally coded as tornado only, that the building code was written for a different loading regime. This interpretation says the mismatch is structural. It is not incremental. It cannot be closed by adding a tag here or running a better model there. It requires a fundamental re-engineering of how the United States warns for non-tornadic severe wind, a re-engineering that would touch the WEA system, the siren doctrine, the building codes, the emergency management training protocols, and the public communication strategy. And that re-engineering is not underway at anything approaching the scale or speed the evidence demands. 3 interpretations, 3 readings of the same evidence base, and the data doesn't tell us which one is correct. That is an honest admission, not a dodge. What the data does tell us, with precision, with specificity, with peer-reviewed certainty, is exactly what each interpretation costs if it turns out to be wrong. If the reassuring interpretation is correct, and you act on the concerning one, the cost is investment in warning infrastructure and public education that turns out to be slightly premature. Money spent, systems built, lives perhaps saved at the margins, but no catastrophic loss avoided because no catastrophe was coming. If the concerning interpretation is correct and you act on the reassuring one, the cost is measured in the way we've measured it 3 times already in this investigation. In power outages counted in the millions, in damage measured in the billions, and in lives lost inside warning polygons that delivered information without urgency. Part 17, what we know and what we don't. There is a way to hold all of this honestly, and it starts with being precise about what sits in which column. The evidence I've assembled over the course of this investigation sorts into 3 categories, and I'm going to name them clearly because precision about uncertainty is the only thing I can offer that actually helps you evaluate what you've heard. Confirmed, and by confirmed I mean supported by multiple independent data sources, replicated across studies, and not seriously disputed in the peer-reviewed literature. Straight-line winds are the single most common severe weather hazard in the United States. Over 15,000 damaging reports per year, 2/3 of all severe weather reports nationally. The destructive WEA tag triggers for approximately 10% of severe thunderstorms. 90% pass through the automated warning system without activating a phone alert. QLCS tornado. Probability of detection is 49%, roughly a coin flip, with average lead times of 12 minutes and frequent 0 or negative lead times. The geographic footprint of damaging straight-line wind events has expanded nearly 5-fold over 40 years, at a rate of approximately 13% per degree Celsius of warming. The I-95 megalopolis houses 53 million people, on less than 2% of the national land area, directly in the expansion zone identified by Prain's analysis. Every major derecho case study in this investigation, 2012, 2020, 2025, exhibited the same failure mode. Warnings were issued, urgency was not communicated, the population was caught exposed. Contested, meaning published researchers hold different positions. The evidence is directionally strong but methodologically incomplete, or the answer depends on institutional decisions not yet made. Whether warn-on forecast can operationally extend QLCS wind warning lead times beyond 30 minutes. The science is promising. The prototype systems demonstrate skill in generating probabilistic wind forecasts at convection resolving scales. But the transition from research to operations in the NWS system involves technology transfer, forecaster training, public communication redesign, and funding that has not been secured. The timeline is genuinely uncertain. Whether the climate signal will increase derecho wind intensity in addition to geographic area. Squitieri's pseudo-global warming simulations suggest the area effect dominates, the footprint gets bigger, but the peak winds don't necessarily increase. Other modeling frameworks and different warming scenarios may yield different conclusions. The intensity question is open in a way the footprint question is not. Whether the 2025 SPC derecho definition revision will meaningfully improve operational communication and public understanding. The definition is scientifically tighter. Whether it changes forecaster behavior in the warning office at 2 a.m, or whether it reaches the public in any form that alters their response to a severe thunderstorm warning, is a sociological question the meteorological community cannot answer on its own. Whether alert fatigue is a solvable constraint or a permanent barrier to expanding WEA coverage for non-tornadic wind. The NWS believes the fatigue risk is real. Communications researchers believe the current system underwarns. Both are probably right, and the optimal policy sits somewhere between them, but where exactly nobody has demonstrated convincingly. Unknown, meaning the data that would answer the question does not yet exist because the test hasn't happened. Whether the next major I-95 derecho will trigger destructive WEA alerts in time to make a measurable difference in casualty outcomes. The answer depends on whether peak winds cross the 80-mile-per-hour threshold at the right location within the right WFO's coverage area, whether the forecaster on duty applies the destructive tag in real time under operational pressure, and whether the WEA reaches phones before the wind reaches homes. The latency in the WEA delivery system, typically 30 to 90 seconds from issuance to phone, may or may not matter depending on how fast the gust front is moving. We don't know until it happens. Whether public understanding of severe thunderstorm warnings will change without a catastrophic event on the I-95 corridor forcing the reckoning. Communications research consistently shows that public risk perception for weather hazards changes most dramatically after direct personal experience with a near-miss or direct hit event. Sustained education campaigns can move the needle, but they require funding, duration, and media saturation that the NWS does not currently have the resources to deliver. The honest assessment, public behavior is unlikely to change at scale without either a massive, years-long education investment or a disaster. Whether the NWS will lower the destructive threshold, create a dedicated derecho or extreme wind WEA category, or implement other structural changes to the automated alert pipeline before the next major event. The institutional conversation is happening. I've seen it in conference presentations, in working group discussions, in the cautious language of agency communications. The institutional action is not yet visible at the policy level. There are 3 columns on this ledger: what we know, what we're arguing about, and what we can't know until the atmosphere tests the system again. And the atmosphere will test the system. The only open question is when. Part 18, the Close the SPC Day 1 Convective Outlook for June 3rd, 2026 used the phrase, "the wind threat should be the main concern." That phrase, embedded in a routine forecast discussion, is doing exactly what every piece of evidence in this investigation says will happen. The system is flagging the threat in technical language that the public doesn't read through a warning product that doesn't trigger a phone alert for an event that doesn't activate a siren. The gap is there. I've shown it to you through the warning tiers, through the detection statistics, through the physics of the rear-inflow jet, through 3 case studies spanning 14 years, through the building codes, through the tree canopy, through the grid vulnerability, through the climate data, and I've shown you that the people working inside the system, SCORE, the service assessment teams, the Parallels researchers, the Warn on Forecast developers know the gap is there. They're working on it. The question this investigation cannot answer is whether the work will outpace the weather. The atmosphere is not waiting. What I can tell you is what to watch. The SPC Day 1 through Day 8 outlooks. You can pull them up yourself at spc.noaa.gov. And I'd encourage you to start reading them the way you'd read a hurricane advisory. The Warn on Forecast developmental milestones, when they cross from research to operational, that's the institutional signal that the paradigm is shifting. And the WEA policy decisions, whether the NWS lowers the destructive threshold, whether a dedicated QLCS or derecho alert category enters the system. Those are the 3 indicators. If any of them moves, the story moves. And if you've stayed this far, through the physics, through the case studies, through the 3 interpretations, through the debunking, through the engineering codes, and the climate data, and the probability of detection for a type of tornado most Americans have never heard of, then you're part of the reason this investigation exists. The people who watch these videos aren't passive consumers of weather content. You pull up the SPC page yourself. You check the meso-analysis, you read the area forecast discussions, and notice when the language shifts from routine to urgent. You understand that the atmosphere doesn't respect the categories we impose on it, and you would rather know the truth of what the data shows, including the parts that are uncomfortable, including the parts where I've told you the evidence is uncertain, than be given a simplified narrative that protects your comfort at the expense of your understanding. That's the community this channel was built around. And when this story moves, when the next QLCS organizes along a cold front in the Ohio Valley and turns toward the most densely populated corridor on the continent, we'll be here, watching the same data, reading the same discussions, following the same evidence, and telling you what it means without fear and without exaggeration, the way we always have. The wind doesn't care about the calendar. It doesn't care whether the siren sounds, and the people in its path deserve a system that warns them with the same urgency whether the wind rotates or not. We'll be watching.